So that was the frequency doubling. I said that I would get back to the laser diode, and that's actually that's going to be fairly easy, because this is exactly the same process as we looked on for light emitting diodes. We have electrons and holes, and when they recombine, they emit the energy in the form of light. So there are different kinds of laser diodes, and we will go through a few different kinds of laser diodes since they're so important for laser spectroscopy. So let us build up a laser diode step by step. And in this case, it's a so-called Fabry-Perot laser diode. It will become clear why we call it that a little bit later. So we start off saying that we have a p-doped region here, we have an n-doped region here, and we have a narrow gap in between them. And that means that by passing a current through this, we can invert the population in this depleted region in the middle, and we can have light coming out. Now, we can have light coming out anywhere along this plane, and we don't want that. So if we make this narrow enough, we in one plane limits it to a single mode. But we would like to limit it to a single mode in two planes, much like a single mode fiber. So that means, to do that, we want to create a waveguide where only one single mode can live. And that means that we also want to confine it in this direction here. We have already confined it in this direction by making the layer thin, but we want to confine it in the other direction. And there are two popular ways of doing this. One of them is called gain guided, and the other one is called index guided. And we'll start here with the index guided. So here you simply make some structure inside your material, which means that your index of refraction will be slightly different for this region here. And this is of course exactly the same way as you make a normal optical fiber, where you have slightly different index of refraction for your core than for your cladding. That means that you can confine it along a line like this. The other version of doing it, gain guided, I don't have a picture of, but the way to do that is that you put a narrow electrode, and that means that you only pass current through in a very narrow part, and that means that only that part will be, only there you will create an inverted population, and that means that it will only lace along that line. And then in many cases you are actually doing both, because why would you like to invert population outside the region where you want the lacing to occur? So you do both. Okay, so now we have created a waveguide, but if we want to create a Fabry-Perot laser, then we want to create mirrors on it so that we can get it to lace on a single frequency. So we would like to have one mirror on this side here and one mirror on this side here. And it turns out that these materials have so high index of refraction that if you just cleave them, they have about an index of refraction of 3. So that means if you just cleave them like this, you will get a 25% reflectivity. And laser diodes have so high gain, in contrary to lasers like helium neon lasers, which have very low gain and you need very highly reflecting mirrors. It's actually enough with 25% here and 25% here to get the thing to lace. And your laser will bounce forward and back, and you will get a standing wave like you show here, and you will have laser emission coming out like this. Now, often, especially if you want higher power lasers, you would of course in this case have emission in this direction as well, and you would like to be able to get all your emission out in one direction, so you will apply a high reflectivity coating to this side, just like we looked at before when we looked at dielectric mirrors. So you can just apply you can evaporate on dielectric mirrors onto these facets, and then you can create a highly reflecting mirror on this side. And actually 25% can often, for high power laser diodes, be too much reflectivity, and then you would lower the reflectivity on this side by applying a partial AR coating, which lowers the reflectivity. So before we continue, let's just quickly remind ourselves about these dielectric mirrors I'm talking about. It's when you have higher index of refraction, lower index of refraction, higher index of refraction, and so on. And that means that on each interface here you get reflection. And if you do it so that all of these reflection adds up constructively, you can get a very highly reflecting. But by controlling this, you can get low reflection, or you can get reflection in any way you want. Or it's very flexible. So we're going to look at a few different kinds of laser diodes, and I have summarized 4 of the most common ones in this slide here: the distributed feedback laser, the distributed Bragg reflector laser, the external cavity diode laser, and the vertical cavity surfacing emitting laser, and also some of their good and weak sides. But let's start with the distributed feedback laser. So in the distributed feedback laser, so to start off, it looks like this. It's a very simple laser. It's packaged in a small package like this, and it's also very popular for telecom, but it comes in other wavelengths as well. And the way it's done is that you have one of these inverted ray in your gain region. And then you have made it so that it's a waveguide in the direction into the board, which I don't show here. But then along the length of it, you have created so that you have created some structure which generates high index of refraction. So that's these blue dots up here. So they are generating turnwise high index of refraction, low index of refraction, high index of refraction, low index of refraction. And that means that you actually have like a mirror going through the whole continuous here. So the part over here will be reflecting in this direction, and part over here will be reflecting in this direction. So it's like a mirror with lacing inside the mirror. And you also have high reflecting mirror on the end often, and then you have AR coating on this side, so you just want to get the light out on this side. And then you send from this yellow thing up here, which is the electrode. You send a current going through the red gain region, and this generates the light. Now, if you change the current, then you will tune the laser because of 2 effects. Firstly, the index of refraction will change because when you change the current, the temperature of this region will change, and that changes the index of refraction. And also it changes the charge carried to density, and both of these things will make your laser tune. So that means that you can tune it by changing the current. And the range you can tune by this electrical tuning is typically about 50 gigahertz. And you typically get 1 to 10 gigahertz per milliamp, and the typical speed, how fast you can, if you want to sweep it forward and back like we wanted to do when we were doing spectroscopy, you can do that with about 10 kilohertz. But you can also move it further by changing the temperature of a whole package. And then you can do that's called thermal tuning, that's up here. And then you can typically tune it a few nanometers. And this you can only do fairly slowly. So the tuning here is about 10 to 25 gigahertz per Kelvin, but you cannot do it very fast, because you can't. If you change the temperature of the package externally, it takes a while before this temperature evens out, so that the inside of a package gets the right temperature. So what is the downside with this kind of diode? Well, the problem with this kind of diode for spectroscopy is that you change the current, and the current also creates the inverted population, which is your gain. So when you change the current, that also changes your gain, and that will change the output power of your laser. And for spectroscopy purposes, it would be even better if you could only change the frequency of a light without changing the intensity of a light coming out of a laser, which brings us to the next kind of laser we would like to look at. And this is called a distributed Bragg reflector laser. And here what you have done is you have separated so that you have 2 electrodes, and this part over here you have a gain, and in this part over here you have a distributed Bragg reflector. So it's the same kind of reflector as the last time, but you have changed the index of refraction, but in this part you have made it so that you have no gain. So when you change the current through this, you will change the temperature and the charge carrier inside this, which will change change the index of refraction for the mirror, which will change what wavelength it reflects, but you won't change the gain because that's a separate part. And again, here you have a high reflecting, I forgot to draw that, but you have a high reflecting facets over here, so that's one of the reflecting, and then the other reflecting mirror is wavelength selective. over here. So both of these kind of lasers can be very good for spectroscopy, but they are not available at all wavelengths. So therefore, another kind of laser which have become very popular for spectroscopy is the so-called external cavity diode laser. So in this case, you take a Fabry-Perot laser, which are available at many more wavelengths than the lasers I just described, and then you create a wavelength selective feedback which selects what wavelength it should lace on, and you make it externally. And so to stop this thing from being a laser cavity diode itself, you apply some way of doing AR coating on the side of a facet. And you can also cut the facet in a Brewster angle so that it has no reflection, and that has become increasingly popular lately. So that means that you have your laser cavity built up by a mirror over here, and then here you have a very high AR coating, so typically only 1 part in 10 to the minus 5 or something like that is reflected back, so this is a very poor cavity. And the light out of this facet expands, you collimate it with a lens, and then you have a grating over here, and this grating selects only a small wavelength band which is fed back, and by changing the angle of the grating you can select what wavelength is fed back. You remember when we looked at a grating in a lithro angle earlier, this sends back one wavelength straight back in the direction where the light comes from, and the wavelength it selects back is the wavelength where it's half a wavelength between one facet and the next. So by changing the angle of this, we can change the distance between the facet in the direction of the beam. So here is a picture of a real external cavity diode lasers. And there are several companies who sell these external cavity diode laser with many different wavelengths, and they are sitting inside a housing, and they are very stable and really good, but it's not so easy to see what's going on. So I chose this one because here this is a modular design where you can actually look inside and have a look what it looks like. So here, this part here is the gain chip. So inside here sits the Fabry-Perot cavity, and on this side here is probably cleaved at an angle, because on this side you see the fiber coming out. Oh yeah, so there's a fiber which is butt coupled to the other side, so that you get the light, in this case, coming out immediately into a fiber. From this side here you have put a fiber right next to this, or you have put a lens and then focused it into fiber, so that light comes out into this fiber here. But on this side, and then since it looks like the active region probably lies in the direction of a chip like this, and then you see over here you have a lens at an angle. So that means that they probably have used this trick where they cleave it at an angle to get no reflection by using it, cleaving it at the Brewster angle, and that way get no reflection. And then you have a lens which collimates a beam which goes straight down, and down here sits your grating in a lithro configuration, sending the light back. And over here you have a motor which can push on this one, and it sits at a pivot point over here, so it turns around this point over here, and when you push at it, it changes its angle here, and that changes the angle of a grating, which changes the wavelength of your laser. Now the last part here is this thing over here, which they call the mode hop adjuster. And what that does is it moves this point on where grating turns. And if you put this just in the right place, you can tune very far without getting any mode hops. And I thought I would try and explain a little bit why this is and how it works. Okay, so here is a number. Here we have a number of different scenarios of how to move a grating. So we have a grating here, and we're thinking about what does the tuning look when we move a grating in different ways. So in the first one here, we take the grating and we move it straight back. Well, we have you remember we had a node on each one of these, on each groove we had a node of a standing wave pattern inside it. So if we move this back, we have a number of standing waves inside it, but if we move it back, all of them will stretch. So that will tune the laser. So you see here the laser starts to tune like going up here. But after a while, what will happen is that since this wavelength doesn't change direction, that means in principle you're feeding back the same overall frequency, and after a while it will be more favorable to lace with a different number of nodes inside the cavity, and you will get a mode jump. So it will jump back. So here you, for example, if you have 6,000 nodes inside the cavity here, then for the next one here, over here, you have 6,001. And then for the next one you have 6,002. Now in fact when you actually tune it, it doesn't quite look like as nice as this, but you do get this mode jump structure. Now the next way of moving it is in one we have in this picture here. Then we think about moving the grating straight back. And then if you don't look at it a little bit more carefully, you might think that, well, okay, if you do that, the cavity will also become longer, so it will tune in the same way. But that's actually not true. And the reason is, if you look on one particular groove here, this groove doesn't become further back, and this groove doesn't come further back. So you change the cavity length without changing the length to each individual groove. And if you do this, that means you get no tuning. So you get this thing over here. And then the next way you can tune your laser is by choosing a point in the middle here, and you turn the grating like this here and like this here. That means that you don't make up here you make the cavity a little bit longer, down here you make the cavity a little bit shorter, but on average you don't change the length to the grooves. But you do change the angle. That means that after a while it will actually be more favorable for the laser to lace with a different wavelength inside the cavity, and you will get a mode hop. And that means that you get a tuning which is basically jump like this, and then it stays at one wavelength, and then you get a jump like this, and then you stay at one wavelength. So then you can jump-wise move far. So to get a mode hop free tuning, that means you don't want these jumps. What you have to do is actually tune around a pivot point like this, and that's this pivot point adjuster here to move so this is exactly in the right spot. Why does this work? Well, the condition you should fulfill to get it to tune mode hop free is that up here you have more nodes, right? There are more nodes in the top and fewer nodes at the bottom. And to get it to tune mode hop free, you should elongate it so that each node in the top here are elongated the same as each node at the bottom. And that means that the elongation should be proportional to the length of the cavity at each point. And one way of doing that, there's other solutions, but one way of doing that is by tuning it around a pivot point like you see in this picture here. And by doing this, you can get mode hop free tuning over tens or even sometimes 100 nanometers. So very, very far tuning over a very large wavelength range without the laser which is tuning mode hop in the tuning laser. Now a downside with this kind of tuning, which is shown here, is that it cannot be done so fast, because you have to mechanically change the position of the grating, and since this is slightly a bit more heavy, if you should do that very fast, it requires a very high force, and then it's difficult to do it in a very precise way. So another way of tuning these external cavity diode lasers is by putting an electro-optic crystal inside the cavity. So an electro-optic crystal is a crystal which, when you apply an electric field over it, which you can do by, for example, putting electrodes on the outside of it, it changes its index of refraction. And this you can do very quickly. So by having such a crystal inside the cavity, applying a voltage will change the frequency of a laser. But now this is corresponding to moving the grating straight back, because you change the index of refraction the same amount everywhere inside the cavity, which means that you are limited, your mode hop free tuning range is limited. But there are tricks to actually designing this crystal so that you can tune over a large wavelength range as well. And if you're interested in this, you can come and talk to me, and I would be more than happy to talk about how you can do that. The next kind of laser I would like to talk about is a vertical cavity surface emitting laser. So here you're actually making layers in this direction instead, and these are the mirror layers. And then you have a thin gain layers, and then you make a whole stack of layers which are your mirrors again. And this kind of laser, they can have a fairly large mode, and since they have large mirrors, they can still have a single, it can come out as a single nice mode. And these lasers are very cheap to produce, so that's really good, and they have good tunability, so in principle they're good lasers for spectroscopy. The downside is that they are fabricated to the wavelength they should be, so they don't exist in all wavelengths, and the output power is typically not very high from vertical cavity surface emitting lasers. And if you remember back to when we talked about shot noise, if you want to do very precise measurement, it's good to have a lot of light, especially if you have samples which are highly absorbing, so that you or highly scattering, so you get very little light out from your sample. The next laser I'm going to describe is as an example how you can use lasers developed for other purposes for spectroscopy. In this case, you see the laser looks very much like a DFB or DBR laser, but this is a very special laser which is developed for telecom application originally. And this laser can be tuned between 1532 and 1563 nanometer, which is a very large wavelength range with only electrical tuning. It can be tuned really fast if in 50 nanoseconds, and it can be tuned anywhere within this wavelength and then scanned so that you can do laser spectroscopy with it. And it works a little bit like a DBR laser in that it has a gain region, and then it has a reflector region, and you have separate input to the gain region and reflector region, so you can control the gain separately, and then by controlling the current to the reflector region, you change, in this case, mainly change the carrier density, which is a very fast tuning mechanism, which allows you to tune the index of refraction. And if you tune the index of refraction, then the optical length between the reflecting parts here will change. So that means that what wavelengths is fed back by this distributed Bragg reflector varies. Okay, so that was this part over here and this part over here. But there is also another one of that another reflector. So that means there are two reflectors. And these two reflectors can be controlled individually. And they are connected together. The reflection from these two are connected together with something called a multi-mode coupler. So you get reflection to the gain region from both of these regions. So let's look a little bit more careful on the right reflector, on the left reflector. So here the reflection from the left reflector is painted in red, and the reflection from the right reflector is painted in blue. And you can see that they have slightly different period. So that means that the separation is slightly different. And right now, the only two which match up well are the ones here in the middle. And that means that the total reflection looks like this, and you have a strong reflection at one wavelength, and that's where the laser, since it's a winner-take-it-all process, that's where the laser will lace. If you now change the current to both of these inputs together, what will happen is that you will move both the left and the right, the wavelength for both the left and the right slightly. So for example, you can change them, and both of these two will tune from here to here. So that allows you to tune over about 50 gigahertz without mode hops. But I said that you can tune over a much wider wavelength range than this. And the reason to this is, what happens now if we only tune one of the gratings? Let's say, for example, we tune the left grating, the red one, just a little bit. If we just tune that, then these two will be overlapping. And that means the laser will now be lacing in this region. And if I only tune the left one a little bit more, these two will be overlapping and none of the other ones. And this is called the Vernier effect from the Vernier scale on a caliper. And again, so if we now tune only the left one a little bit, so that these two, for example, is overlapping, and then we tune both of them, then we can tune from here to here. So this allows us to make a jump really quickly and then do a co-organized scan and then make another jump and do an organized scan. And we have an example of spectroscopy made with this technology. So here we have carbon dioxide, which absorbs over here at 1560 something 5, and then we have methane, which absorbs over here at about 1537 nanometers, and then we have carbon dioxide, which goes a little bit lower, and then over here we have acetylene at close to 1534 or something. So by jumping between this and each place like this, you are creating a scan, and then you're actually modulating as well, because you want to do very low noise detection. So you first scan at this range here, and then you scan at this range, and this range, and this range. And that allows you to detect all of these gases in as little time as you see here. This is only about 25 milliseconds, and then it starts all over again. So in a very fast scan, you can jump between and see changes over a short amount of time by jumping between where the different gases have their absorption features. While we are talking about diode lasers, I would also like to show you that diode lasers are not only used for spectroscopy, it's also used for a lot of other things. And diode lasers can have very high power. So for example, this here is a big laser facet, so it lasers from the whole of this facet, and it has a peak power of 800 kilowatt, this laser diode. And by pumping fiber lasers with laser diodes, you can get fiber lasers which continuously can send out up to 500 kilowatt of light through a single fiber. Not a single mode fiber, it's a multimode fiber, but a single fiber nevertheless.